not only am I not in a good mood, but the textbook does something I don't like. And I missed this last year because last year, right around this time, was when we had some flood or something or other. So this was the week that we had missed this time last year. And so I didn't teach this chapter in class. I did it online. And then looking through the lecture notes for today, I realized this person, whoever wrote this textbook, can't even say his name. Let's call him Howard. Howard, I don't like what he does in this chapter. And then I'm thinking, well, geez, you just made a bunch of students read this chapter. I know none of you read it, but still, right? You better take some time today to explain why you don't like it, but yet at the same time be your calm, reassuring self and actually teach them some math. So we'll see how this goes. Because again, I practice on you guys. Thursday class, that's when I have this down. So what this chapter does is we're trying to make a pivot. We're trying to turn to make the statistics that we've used just a little bit more useful. And last class, we talked about the area under a curve. And the area under a curve is how much? 1. And how often is it 1? Always 1. And 1 is a great number because we can use that 1, maybe turn it into 100 and use it as a percentage, or we can use it for probability because probability of an event happening at most is 1. So this chapter tries to make that pivot towards probability and using curves and the area under the curve to represent the probability of an event happening. Then the son of a bitch comes and gives you a brand new distribution. I've just spent like 3 weeks talking to you about a normal distribution, chapters 3, 4, and 5, and then Howard's like, haha, watch this. Here's a binomial distribution. Doesn't he know that I'm dealing with you people? You math-phobic people? So I'm going to be nice, and I'm going to teach the chapter and teach you about a binomial distribution and show you some really scary math. But that's okay, because you like me, and we're going to calmly work our way through it, because it's always bucket on the floor.
Do we have to use this on the midterm?
You will be given a fresh one for the midterm. All right, so let's talk about probability for a second. Probability, again, concept that you learned a long, long time ago. The probability is the likelihood. I love it when you define a word with a word that means exactly the same thing. Likelihood of an occurrence of an outcome of an event. Man, Howard's really pissed me off today. Of occurrence of outcome of an event. It's a horrible sentence construction. Given all possible outcomes. So if we want to write this as an equation, P stands for probability. In parentheses is the event that happens. Equal to the number of ways an outcome can occur divided by the total number of possible outcomes. The sum of all probabilities is always 1 or 100%. And there's this thing about the addition rule. Probability is kind of weird. It's kind of like multiplying. When you have mutually exclusive outcomes, the probability of the outcomes can be summed to find a combined probability. So let me explain this for a second. Vegas craps, the one with the dice. Lots of games in Vegas and gambling are just built upon probability. So when you're rolling dice and craps, what's the number you don't want to get? What's a bad, oh my God, you babies. Come on, you've never played craps before? Good, because it's really hard and it doesn't work to your advantage. The bad number when you roll dice and craps, 7. Let's just say when you roll a 7, you lose. Well, why did Vegas pick that number of all of the possible numbers between 2 and 12, 2 1s and 2 12s, 2 6s equals 12, why did they pick 7? Because it's the what? Yeah, it's the most likely to occur. Why? Because think of all of the ways in which you can get a 7. You can get a 7 from a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, and a 6 and a 1. So 7 has the highest probability of being rolled when you roll 2 dice. So it's the most likely outcome. And that's a good thing to put as the loser if you're Vegas, right? The most likely outcome, because you're trying to win everybody's money. That's the addition rule. Because what you're saying is that the probability of rolling a 7 is equal to the probability of a 1 and a 6, that plus a 2 and a 5. Got this? Okay, thank you. That's your basic reminder about probability. Why is it important to us? Well, we need probability because what we're doing in statistics is based off of the idea that we have a sample. Our data is most often a sample. And that sample is drawn from the larger population. We start getting into probability when we think about the fact that our samples can be imperfect representations of that population. So that's why probability theory is important. We need to figure out how it is that we can understand our room's sample shoe size relative to the population's sample shoe size. Now let's think about the qualities of our room. And everybody take a look around at everybody else's feet. What are we missing about the average shoe size in our room? How are we missing that, though? Anna? How is it that our sample is missing something from the population?
Kids.
What do you mean, kids? Like, how are we missing those? Yeah, we don't have any kids. We have 0 children in this room. Have you seen the size of shoes that children wear? No, because none of you are probably parents and have to buy their ridiculously tiny shoes all of the time. John. Shoes are that big. So our sample of this room is imperfect. It is not the best representation of the population, and we need to account for that. So the way that we do that is by probability theory. Given a sample shoe size of average of 8, what's the probability that we would get that average shoe size of 8 from a larger population? Beats the hell out of me, but I got to use the word probability in my example. So that's why we need to have some working understanding of it. We can do this the same way with probabilities and z-scores. Because remember, a z-score is just converting your raw score to a standardized unit. So when we ask what percentage of scores is between 0 and 2.4, that's saying the same thing as if we were to randomly select a z, what's the probability that it's between 0 and 2.24? As if we just go around randomly selecting z-scores for fun on Friday nights. Hey, let's play a game. Play a game. Okay. Give me a number between -3 and 3. Nah, that's not any fun. If you think it's fun, you're doing college wrong. But it's actually saying the same thing. How many people have I lost? Halfsies? All right. Well, let's think of it this way. Remember, the area under the curve represents 3 things at once: area, probability, and percentage. And a lot of times when we say percentage, because it's between 0 and 1, a lot of time we're also talking about probability. So if I were to say, what's the probability of getting between 0 and 2.24, and we think about the area of that curve, and I express that as a percentage. So let's say it's, well, I don't know, let's look it up. (2.2) over to 4. Let's see, that's 98.75. I gotta subtract a half because I got that 0. Remember, I gotta look at the drawing. So that's what, 48.75? So the area is 0.4875, but the percentage is 48.75% of my curve, and the probability of picking a number between 0 and 2.24 is 0.48. Why? Just is. I just did. Yeah. Yeah. What's the probability? So let me use the example. Let's get to this Howard stupid example. So this would have been great if Howard would have stuck to our normal curve, but he didn't. He had to throw in a distribution known as a binomial distribution.
So you could use a normal distribution for this? Absolutely.
Area under a curve is area under a curve no matter what the shape of the curve is. But for some reason, Howard says, well, instead of doing an example with a normal curve like we've done for the last 3 chapters, let's introduce them to a new distribution that we rarely, never, ever use. It's called the binomial distribution. And I understand kind of why he did it, because it's the simplest distribution to understand. The binomial distribution is the one that reflects a coin flip. So how many outcomes do you have with a coin flip? 2. Right? We can do enough with fingers and toes to understand this. All right, let's play along with Howard's game here. So binomial, bi, B-I, 2, nomial, kind of like nominal, right? Binomial distributions have only 2 categories. There are dummy variables, our light switches, where you're either on or you're off. Let's stick with the coin, heads and tails. The probability of an event happening can be labeled as a P and a Q. This is not where the expression mind your P's and Q's comes from. So we can have one outcome that's a head, and a second outcome that is tails. And because math is fun, we can remember that all probability sums up to 1. So P plus Q equals 1. and P equals 1 minus Q, or conversely, Q equals 1 minus P. Again, let's take something really simple and make it look confusing and hard. P and Q, heads and tails. And here's really why I don't understand exactly what Howard's doing. The binomial distribution looks a hell of a lot like a normal curve. In fact, the more sort of trials you have, the more times you flip that coin, it's going to really, really, really look like a normal curve. All right. So what I wanted Howard to talk about this chapter, now that we got that basic, really simple idea of probability and our little sidetrack with the binomial distribution down, really what we need to start doing is talking about how we can use our curve and the area, percentage, and probability that we can generate from that curve to start testing hypotheses. For all of you that have been wondering about why hasn't he talked to us about the course paper yet, it's because you haven't been told anything about the skills that you need for the course paper yet. We're about there. Because what we do as social scientists with hypothesis testing is we take our sample data and we say, given what we know about our sample, what can we say about our population? I'm a political scientist. I like to talk about voting, whether it's judges voting, citizens voting in elections. Political scientists love voting. Members of Congress voting on bills. Voting's everywhere. So if I were to take a sample from this class about an election that's upcoming, I'd have to understand how my sample relative to the population behaves. That's where probability theory and the curves all come in. So I did this last fall. There's a type of variable known as a feeling thermometer, where you ask an individual on a scale of 0 to 100, how do you feel about an individual? And we did it with Hillary Clinton. And I think the average Clinton thermometer score last year was like a 35. People just did not like Hillary. But then I compared it to a larger sample. I compared it to the General Social Survey. And it turns out that our class last year was abnormally anti-Hillary. It just was, I think the average Hillary score in the larger sample was like 60 something. And we were, whoever, the students in my class were, their average had a very low probability of representing the sample. So I framed this in terms of, are you people normal? And they are not normal. They were not normal. You guys are probably cool, but they weren't normal. So my research hypothesis, I was trying to see if our class was normal. Was the people in my class, were the people in my class normal? But statistically, I had to focus on their mean relative to a population mean. So I'm focusing on the mathematics of it. And that's what allows me to test my research hypothesis. So the two work together. in order to do research hypothesis testing, we got to follow a series of steps. And this is what allows us to put that term science in political science or social science. If we follow the same procedure every time, we're scientific. So the first thing that we have to do, one, state the null and alternative hypotheses. So I probably better teach you what those two things are. But I know you all loved slide copying, so I'll actually just read the slide to you so you can copy it down, and then I'll go over it. Step two, we'll have to make a decision about that null hypothesis. Notice we're not making a decision about the research hypothesis. We're focusing on that null hypothesis. Once we make a decision about the null hypothesis, we're going to draw a conclusion from our analysis. And then finally, we're going to relate the result of the analysis to our research hypothesis. So these are the 4 steps in hypothesis testing. This is what you're going to have to do in your papers. You're going to have to demonstrate this, your ability to do this. All right, so let's start. 2 types of hypotheses. Now, these hypotheses should be mutually exclusive, which means if you're one, you can't be the other. Mutually exclusive. Can anybody think of 2 categories that should be mutually exclusive? If you're one, you shouldn't be the other. Or you can't be the other. Maybe. Should be, right? Right? 2 mutually exclusive conditions. Can you be a police officer and not a criminal? All right, you keep thinking on that. Cat and dog, fine. If you're a cat, you can't be a dog. Okay. I'll go with that one. I was thinking married and dating. If you're married, you best not be dating. Right? I know. Hey. Trying to think of, mutually exclusive. Think of like sports fandom. Like, I'm a Boston Red Sox fan who respects Derek Jeter. No, it doesn't work. If you're a Red Sox fan, he's overrated. I know that because that's what they chant. Overrated. He wasn't really that good of a shortstop. All right. Mutually exclusive. So hopefully when you set up your null hypothesis, your alternative hypothesis, they shouldn't both be able to be. Like, here's a math example, you are either odd or even. You're not both. All right. Null hypothesis. Usually when we think of the null, we say that there's no effect. No effect. Now, again, this is where I quibble with Howard. Because the example that he uses throughout the book, his book that is titled, by the way, Statistics in Social and Behavioral Sciences, is about a football game. Why? Of all the science that goes on about people's behavior, why did you have to choose a football game? But he did. So this is my life today. he uses an example about whether or not winning the coin toss of the Super Bowl has an effect on winning the Super Bowl. You're shaking your head. You're like, oh yeah, absolutely. We're not talking about overtime. We're talking about the initial one. You see, got some heads shaking. You're like, no, that's crap. So that's the hypothesis we're going to investigate. Does a football team winning the coin flip increase their likelihood of them winning the game? I got yes and no's. Well, let's figure it out. So the null hypothesis would say, and again, this is so awkward. Why did he choose this example? That there's no relationship between winning and the coin flip. So awkward. So he says, let's look at a sample of a dozen games, 12 games. If the coin flip doesn't matter, on how many of those, if there's no relationship between the coin flip and whether or not you win the football game or not, how many games should a team win out of 12? He says 6. Why 6? It's half, which means half would win and half would lose, because there's no relationship. That is so counterintuitive to actually pick an exact number. But okay, it's his example. Let's roll with it. So his his null hypothesis is that the average number of games won out of 12 would be 6. And that would show that there's no relationship. You still with me? Again, I don't like this example. The alternative hypothesis, we actually number our alternative hypotheses, because you can have multiple hypotheses. You can have 2 or 3 different alternative hypotheses. You have at least 3 in this example. This is where you're actually testing that a relationship exists. So it's an alternative to no relationship. So in our example, our alternative hypothesis, H1, is when mu does not equal 6. Now, just before we go on, should the coin flip be an advantage, winning the coin toss, should that be an advantage or a disadvantage? An advantage, why? Okay, you get to choose if you get the ball first or if you're going to defer to the second half. Okay, so if you're a defense-oriented team, you would want to defer to the second half. Whatever, I don't care. Let's just go back to this. So could it be a disadvantage winning the coin toss? Maybe it gives you a false sense of confidence that you're a winner, and because you won a simple coin toss, that you will then win the game, and then you proceed to get your asses kicked. It provides you with overconfidence. Yeah, I don't know. I'm just coming up with an alternative here. All right, this is where I wish I could remember my greater than and my less than. I think the alligator wants to eat the bigger meal. So we would say that this, you always pick on and point to the lesser. This is known as a directional hypothesis. I'm saying that the coin toss should help me win more than the mean. Right? I should win more often versus I should win less often. You don't have to do this. This is like me stuff. This is what professors do. We use directional hypotheses. So in some of my research, when I was testing the effect of public opinion on judges, should a public opinion that is rights granting lead a judge to vote in the opposite and take rights away from a group? That makes no sense. So I would use directional hypotheses in my research because I would say, well, there's actually a preferred direction here. A standard research hypothesis is either there's no relationship, which is the null, or there is a relationship. But taking that there is a relationship allows for both the positive and the negative effect, which in my case doesn't make sense. But we do this. It's a possibility, something that can be tested. The next step, make a decision about the null hypothesis. Remember, we focus on the null, and we make our decision based upon what we're going to do to the null hypothesis. You have two options with respect to the null hypothesis. You can reject the null hypothesis. So you can say that our sample tells us that there is, in fact, a relationship between winning the coin toss and winning the game. The evidence from our sample or what's the opposite of reject? Yeah, you never do that. You never accept the null hypothesis. You never, ever, ever, ever accept the null hypothesis. Why? Because you only have one sample. What if you get a bad sample? You don't want to accept the possibility that there is no relationship because you're just using a sample. Never, ever, ever accept the null hypothesis. You either reject it or we don't reject it at this time. You're never going to accept the fact that no relationship exists. How are we going to do this, though? How are we going to make a decision about the null hypothesis? Well, we're going to look at our sample. And we're going to compare our sample to our expectation. In this example of the football coin toss Super Bowl stuff, the expectation is we can look at 12 Super Bowls and see if the winning oh God, this is so stupid. If the team that wins the coin flip wins the game. This feels like me talking to my mom about playing the lottery. Like independent events. Okay. So we're going to have to look to see, given our sample, what's the probability that our result can be drawn from the larger population. Now, ideally, we want a low probability, because remember, we want to make it hard to reject the null hypothesis. So we're going to set our decision rule really, really small. And in the social sciences, we actually kind of agree about this. The number that you set your decision rule at, where you're going to reject the null hypothesis, is called alpha. Don't ask me why, I don't really know. and we set alpha to be 5%. We want it really, really hard to reject that null hypothesis. Now, in doing so, in making it hard to reject the null hypothesis, really what we're avoiding is the concept of a false positive. That's what we're trying to do. We don't want to say that there's a relationship when there's not one. Do you understand why that could be bad? Like, what's the worst thing that somebody can tell you about you is positive, and really they're just wrong? We make movies about this scenario, by the way. They're kind of funny sometimes. William, you have 3 days to live.
Hell yeah.
Why would that be bad to be wrong about? Because he's going to do some really stupid but yet fun stuff in the next 3 days, right? There are like 14 different movies about this. They even tried to do a TV show about it, which sounded really depressing. Like some girl's told she has cancer and she has a year to live, and then she still lives, and she's like, oh no, I've ruined my life. Yeah, like people really wanted to watch that on TV. Yes, there are movies and TV shows about this. You're given a diagnosis that is wrong. Right? We really want to be sure about stuff like this. So if I tell you that drinking a glass of wine makes you live forever, I should be really sure about that. So that's what we do in the social sciences. We want to make sure that it's really hard to have a false positive. Now, in order to do that, we're willing to accept the possibility that we miss some relationships. Because if our threshold, right, is down to 5% chance, well, what if we do our results and it turns out that we have a 6% chance? Do we reject the null hypothesis? No, because we said it has to be 5%. So there are times where there will be a relationship and we'll miss it because we have such a high standard. A high standard with a low number. Yeah. Okay. So how do we do this back to our example? Let me turn the lights off. Okay. This up here is our binomial distribution. This is what it looks like. Okay, I can kind of understand why Howard did this. So one of the things about a binomial distribution is that it does have a beginning and the end. Does our normal distribution have a beginning and an end? What's the beginning of our normal distribution and our end? Yeah, they go all the way out to infinity on both tails. So maybe, okay, Howard, you got a little something going on here. You're smart. So this is a binomial distribution of the number of wins out of 12. John?
How is it a binomial distribution though it's not like heads and tails, it's just wins?
Because you have two outcomes, win or lose. And the only thing that we're doing is the number of trials. So how many trials do we have? 12. And how many outcomes do we have in each of those 12 trials? 2. Because you don't have a tie in the Super Bowl. You just keep playing. Does that make sense now? If I wanted to, I could cross out wins and put heads.
Okay.
In fact, what the hell? Go ahead and do that. and it's still the exact same. Right? No matter what it is, the outcome is 0 or 1, and if I have X amount of trials, this is what our distribution looks like. What do you notice about this distribution in terms of shape and numbers and stuff? Is it symmetrical? How would I know if it's symmetrical or not? Okay, it's the same on each side. What numbers? These numbers? These numbers? These numbers? What are these numbers? They're both. It's both the percentage and the probability. So what is the probability of winning 6 games out of 12? 22%. Okay. Fine. 22.5%. So it is both the area and the probability. We want to set our alpha to 0.05, which means we got to be in the tails. How many games would you have to either win or lose to be convinced that the coin flip mattered? How can we figure that out? What, John? Kinda. We could look it up in a table, which is point number 2. But I'm not giving you the binomial table because you don't need it. You can just look at this and go, okay, I can figure this out. Friends? What? What about 12 tries? So you're saying that you would need to win all 12 of 12 to be convinced that the coin flip matters. Okay. How many games would you have to win to be convinced that the coin flip matters?
6.
Why 6? 6 is our null hypothesis, right? But again, we're not just looking for an average number that's more than 6. So let's go ahead and say we look at a sample of 12 Super Bowls. 8 of the coin flip winners won the Super Bowl. Is that enough for us to reject the null hypothesis? I'll tell you right now, the answer is no. Because what's the probability that we need to have to be comfortable to reject the null hypothesis? It's in red. It's up there. 0.05. Okay. Because we're symmetrical, we have to do both sides at the same time. How likely is it that you win 0 of the 12 Super Bowls? Really, really unlikely, right? If you win, all right, if we look and we look at all of the coin flip winners, so Super Bowl 1, Packers versus whoever lost to the Packers. The Packers lose the coin flip, therefore, and then they go out and they win the game. And then it goes all the way up as the Chiefs. I think they beat the Chiefs twice in a row. And the Jets beat the Colts, and then that's about all I got. All right, so we look at the first 12 Super Bowls. The coin flip winner wins 0 of those games. That's like the coin flip winner getting, all tails, and all the tails lose. Again, I hate this example. But how likely is that? Well, it's pretty damn unlikely. And because I did 0, now I also have to do 12. How likely is it that you win all of the games? Also very unlikely. How about 1 and 11? What I need to do is I need to find the numbers that gives me my decision rule. What do you see, Anna? All right, keep thinking about it. That takes that 5% and puts it all out in the tails. Okay. So it is really unlikely to win 10 of your 12 games, 11 of your 12 games, or 12 of your 12 games. It's also very unlikely that you would lose all of the games, all but 1 of the games, and all but 2 of the games.
Would it be wrong to say that you could have came to that conclusion by going to that .05 and just drawing a line directly across if that resulted in
Yes, I could have done that. 0.05 in total.
So that's why it's at 3 and 9 and not 4 and 8.
So I'm taking my 5% and I've split it up and put it in the 2 tails, because most hypotheses are non-directional. So whether or not having the coin flip. So if I have a sample, right, those first 12, and I say that the coin flip winning team wins 9 of the 12 games, well, that actually is okay. That is likely given a distribution where the mean is centered at 6. It's not less than 95% likely. Okay? Bad example. So basically what we do in practice, right? Forget the stupid football example. Damn it, Howard. Messed us all up. Forget the stupid football example. We as social scientists use a 95% or a .05, however you want to look at it, decision rule. You take the .05 and you split it up and you put it into both tails. Now when you do that, you can just look on the table and say, what z-score gives me .05 in the tails? Oops, wrong one. Stop it. We can do that. I know off the top of my head that a z-score with .05 is 1.96. Why? Because that's a magical number for anybody taking a stats class. You got your thing out? Look up a 1.96. What does 1.96 correlate to in the area in the tail on your table? 0.9744.
That was fine. Oh, 0.975.
So basically, we have a normal curve. From here on out is 9750. How much is here in the tails? Don't make me throw shit at you guys. That's half of 5%. 1.96. And this is the reason why I don't like the binomial. Because the binomial distribution depends upon the number of times you flip the damn coin. In this example, we flipped the coin 12 times. If we flipped the coin 8 times, it would be a completely different distribution. I'm trying to teach you guys about the standard normal distribution. I'm trying to get you guys to know this normal curve backwards and forwards, and Howard's like, hey, let's try a completely different curve that has 3 parameters instead of 2. Damn it, Howard. If we're going to create a decision rule and say that you have to have 0.05 to reject the null hypothesis, let's use one where we can cite it chapter and verse, get it tattooed on our arms if we need to, of z being greater than or less than negative 1.96 or positive 1.96. Like, that's the magic number to say that we can reject the null hypothesis. So what do you have? Well, first, you got to find your critical value. Critical value of z is 1.96, plus or minus 1.96. And then when you go and calculate z, and it's outside of that region, you can reject the null hypothesis. For the next, 3 weeks after the midterm, we're going to do nothing but more standard normal distributions, and we're going to be using this 1.96, 1.96. That's our critical value. Critical value of the test statistic, whether it's a mean or an expected value in the terms of a binomial distribution. It's the value that separates the 2 regions. What 2 regions? Well, you have a region of rejection. The region where the combined value of the probability makes up the ability to reject the null. Where is this region of rejection on any curve you draw? Where is it? It's in the tails. It's always in the tails. The region of non-rejection, it's in the middle. It's always in the middle. Again, bucket on the floor. Whenever we're given a question, the very first thing we should do, draw the damn curve. Label it with the values that we have, or the ones that we expect. Find the area, and then compare it with our hypotheses. So for a decision rule that alpha is 0.05 and we have 12 games, the critical value is 3 or 9 wins. So if you're under 3 or more than 9, then you can say, holy crap, that's a magic coin. Otherwise, given what we know about the shape of the distribution and all of the possible events, it's really not that rare for a team to win 9 games. Now, when I say it's not that rare, it's because we have a really stringent decision rule. We don't want people thinking they have cancer and go out and ruin their lives. Go wild and crazy in the next 3 days, right, William? Woohoo! Stuff's going to be on fire. We don't want to do that. So we want to have almost, I don't want to say this word. I want to say certainty, but I don't want you guys to start thinking you can have certainty in a world that is based off of probability, because that'd be bad. You know what I mean? And this is why they use terms like likelihood. Right? You have a really high likelihood. Likelihood's just a synonym for probability. Chance. Well, that's not good. 95% chance. It's not much of a chance. If it's 95%, I'm going to win. But it's so possible that I lose. See, we fight against this type of language, this deterministic language. What was my example earlier? Glass of red wine every day, you will live forever. Will is a deterministic word. If I say you will do this, it's going to happen. Unless you're John and you're 4 years old. You will put your shoes on. He actually laughed at me the other day. Like, you have nothing to say what I'm going to do. He just looked at me and laughed. John, put your shoes on. He didn't point, but I know he wanted to. I would have lost my mind if he pointed at me. Things would have been thrown in my household. I would have thrown his shoes at him if he pointed at me. But instead he just looked at me, smiled, and laughed. Like, you fool. Because we really don't want to do this, right? We don't want to say it's determined. Because that's the bad side of probability. If I tell you that something is 99% likely to happen, that still means you can get pregnant and use a condom. Because there's that 1% chance. Nothing is certain. Son of a bitch, those abstinence-only people were correct. But they don't know about multiplicative probability. All right. Anyways, you get where I'm going here? We like to talk in terms of absolutes, but when we're dealing with samples and populations, there's always that 5% chance, even with the decision rule, that we're wrong. And we try to avoid it as much as possible. But it can happen. Yeah, I did that. Drawing a conclusion. Conclusion should state the sample from whom the data were collected, the value of the statistic. Yeah, you're basically just going over here. Does the analysis support the original research hypothesis? This is where we get into our discussion of proof. Again, we have this problem because proof implies certainty, and nothing in this world is certain when you're dealing with human beings. And what we're doing is we're using our samples to either provide support or lack support for a hypothesis. Again, never use the word prove. You don't prove anything. You find it highly likely that a relationship exists. But you don't prove. Because when you say prove, you're saying that it must happen this way. So when we as political scientists talk about voting, we can find that it's highly likely that Republicans will vote to do X. But it's not certain. In fact, between Democrats and Republicans, Republicans have lower levels of cohesion, attitude cohesion, than Democrats. Some grad school buddies of mine just wrote an op-ed in the Washington Post where they looked at data, and it perfectly explains why Trump can get nothing done. And that's because of the two political parties, he decided to be a member of the party that has a wider range of beliefs than the Democrats. You might not like what the Democrats have to say, but holy crap, when you're a Democrat, you believe and have the correct issue position on 8 out of 10 issues. When you're a Republican, the average number of correct Republican positions on an issue out of 10 is like 6. That's not good. You got lots of Republicans out there that like to spend money on things like education. And so it's harder to work with Republicans as a unit because they're more like this, whereas Democrats are like this. They actually know what it means to be a Democrat, whereas Republicans can justify anything. Well, I'm a libertarian, really. Like, yeah, that was good for an answer. You're now down to 7. All right. When my friends write in like the Washington Post, I love to read the comments because I know that my friends are just going to fly right over all the people that are willing to comment on the internet. And I got about 5 in, and I'm like, oh, not so bad this time. Good job, guys. Because they did a really good job in their article talking about how it is that they use this likelihood, and about how they're not talking about certainty, they're talking about likelihood. We could be wrong. We did talk about this. I told you that there's 2 types of errors, right? There's a false positive, where you find a diagnosis that shouldn't be, and then there's also a lack of a diagnosis, where you say that it's negative, but it should actually be positive. We talked about that. We're going to find out that there's, when it comes to hypothesis testing, first of all, sample size is very important. The sample size introduces something to our analysis known as a standard error. And essentially it says the smaller our sample is, the more likely that that sample doesn't match our population. So we're going to learn how to take that into account. And we're also going to talk about alpha and sort of shifting alpha. I've already mentioned the idea of directional hypotheses. And we can make alpha even lower. So we can make a decision that says, hey, when you're going to tell somebody that they're going to die, instead of being 95% sure, why don't we not, crank that up a little bit? Make it 99%. We can do that. Because then we just have 1% in the tails, and we look up in our table where we get to 99.9900, and that's our new decision rule. So we'll be talking about how we can change the level, because we don't need 95% in all circumstances. Maybe we're Guinness, and we just want to be 90% sure that our beer will get people drunk or taste good. That actually would be advantageous for us. Talked about that. Talked about that. All right, I'm good to go with this.